Hello everyone, I am Prem Kumar Aliki Sivakumar and my matrix number is B122400 So today I am going to explain about introduction. Communication systems enable the transmission of information such as voice, audio, video and data over long distances. Since low frequency voice signals cannot be transmitted efficiently due to poor radiation and susceptibility to noise, modulation techniques are used. This project focuses on amplitude modulation, which is AM, where the amplitude of high frequency carrier signal is varied according to a message signal while the carrier frequency remains constant. A real voice signal recorded through a microphone is used as the message signal and processed using MATLAB. The voice signal is modulated, analyzed in both time and frequency domains and evaluated under different modulation indices and noise conditions. Using a real voice signal provides a practical understanding of how AM is applied in real communication systems and how transmission quality is affected by various parameters. So there are total 8 objectives for this project. The first one is to record and process a real voice signal using MATLAB. Second, to generate a high frequency carrier signal for transmission purposes. Third, to perform amplitude modulation, which is AM, on the recorded voice signal. Fourth, to observe and compare the original voice signal and the modulated signal in the time domain. Fifth, to analyze the frequency spectrum of the signals using fast Fourier transform, which is FFT. Sixth, to investigate the effect of modulation index on the AM signal. Seventh, to study the effect of noise on signal quality and voice intelligibility. Lastly, which is eighth one, to understand the practical application of modulation techniques in communication systems.
A very good day to my lecturer and also my fellow friends. So my name is Nanda. I'll be presenting methodology. Okay, so we are going to go for the methodology, which is the main part of this assignment. All right, so this project was conducted using a MATLAB. Okay, so we're using MATLAB to simulate the AMM modulation and also to communicate the system using a real voice signal. Okay, so the main objective of this methodology is to demonstrate how a voice signal can be recorded, processed, modulated using a carrier signal affected by the noise and analyzed in both the time and also the frequency domain. So communication system has designed to transfer the information from one location to another. So however, low frequency signals cannot be transmitted efficiently over long distance. So that's why the modulation is required to shift the information to a higher frequency range suitable for the transmission. So this methodology will begins with the voice recording signal preprocessing. So we'll record the voice later and you can see the output on the result and also the discussion part. So the recorded voice is then normalized and use the message signal as a carrier signal is generated and also combined with the voice signal through amplitude modulation. So noise is later introduced as simulate to practical communication channel. Finally, the last part, it will analyze all the perform as to evaluate a system performance. Okay, so this methodology is one of the main part of this assignment because it will provide a schematic procedure for conducting this experiment. It is also to ensure all the stages performed in the correct order, and it also helps the readers to understand how the result is obtained. All right, so we are going to go for the flow chart. Okay, so this is the flow chart. Okay, we are starting from the first part. Start, record our own voice. Okay, so ending is the result and discussion. Okay, so this is the flow chart. We have explained about this flow chart of this experimental process. So it provides an overview on this entire methodology in a simple organized manner. Okay, so instead of reading all of the text, you can just read this part first for the first reference. All right, so we are starting from the first part, which is the voice signal recording. So this voice signal recording in the first stage is involved obtaining a real voice signal that will act as a message signal in the communication system. So in the communication system, the message system signal is actually is the information that we need to transmit it. Okay, for example, we can transmit it using speech, music, videos, digital data. But in this experiment, we are using human speech, which means a human will be speaking. Okay, so the voice will be recorded. Okay, so that is, so when a person speaks into a microphone, the sound wave is produced. So this sound wave consists the pressure variation in the air. So the microphone will automatically converts the pressure variation into the electrical signals, where then they are converted into a digital samples by the MATLAB. So the recording we are doing around like 5 second chosen. Why we choose 5 second? Because the signal length manageable for the processing and analysis. So then later, after we recorded, we store in a wave file. So the wave file is preserved in the original waveform without compression, ensuring that the signal characteristic remain unchanged. Okay, so we are using our real voice. You can see the next slide. So this is the MATLAB command. Okay, so we're going to explain line by line. Okay, this is we using our own voice as a human speech. Okay, we are not using recording anything speech or what, we are using our own voice. So you can see line the first line over here, we have explained we are using what is 44100. So 44,100 is the sample per second, and we are using 16-bit resolution. Okay, so each sample represent using 16 bits. So why we are using 44.1 kilohertz? So according to the Nyquist stereo sampling theorem that we have learned before, human hearing extent is approximately around 20 kilohertz. Okay, and then 2 times 20 kilohertz is approximately around 40 kilohertz. So we use 44.1, which is a bit higher, this so that it can satisfy the requirement. Okay, so the next line is record blocking. So this record blocking means it records the voice for around 5 seconds lah. So once the person enter, after write this MATLAB code, he press enter, he can only speaks for 5 seconds. Okay, and then the next part is get audio data. Okay, so this one will retrieve the recorded audio sample. Okay, and this is the thing, and you can audio write. Okay, audio write is to save the recording. Okay, save the recording as voice WAV. Okay, so we're going to go for the next slide. Okay, okay, so the next slide is importing the normalizing voice signal. So after we record the voice signal, the audio file must be imported into the MATLAB for further processing. So after, although the signal can be heard as sound, MATLAB process the signal as a numerical data. So therefore, the wave file must be converted into the sequence of amplitude values. So when the MATLAB imports the audio file, every single sample of the voice signal is stored as a numerical values. So this value represent the instantaneous amplitude of the speech waveform in a different moment in a time. So the amplitude will records the speech so that we can significantly depends on how louder the user speaks using the microphone. Okay, so some recordings, as we know, have a very many large amplitudes, while some may have a very smaller amplitude. So due to the variation can affect the modulation process and make signal comparison much be difficult. So normalizing is an important processing process, because it prevents excessive amplitude variation during the modulation. So without this normalization, the signal could become even too large and lead to over modulation or distortion. So by ensuring consistent consistent amplitude range, the modulation process become more reliable, and then the result become more easier to be analyzed. Okay, so the normalization also allows different recordings to be compared fairly because all signals share the same amplitude scale. Okay, so we're going to go for the MATLAB code on the next slide. So the next slide, we're going to explain line by line for this MATLAB code for this importing and normalizing the voice signal. So the MATLAB code line number one is voice comma fs equals to audio read. So this one explains it reads the audio file and imports into the MATLAB. Okay, and the next one is voice. So voice means it will store the audio sample. Okay, so we have explained this one. The next line, voice equals to voice max abs voice. So this one, it will performs the normalization process. So abs is stands for converts all the amplitudes into the positive values. For example, if the value is negative 0.8, it will convert to positive 0.8. Max abs voice, it is to find the largest amplitude. Okay, so I think this might be understand for you. So we're going to go for the next slide. So the next slide is generation of time vector. So the time vector is one of the most important components in this digital processing because it provides the time reference for every sample in the signal. So when the MATLAB records or imports an audio signal, the signal has a sequence amplitude. So although MATLAB knows how the order of this sample, it does not automatically knows the exact time associated with the sample. So for example, if we have sample 1, sample 2, sample 3, sample 4. So these sample numbers alone, they are alone and not sufficient for plotting a waveform, but because they do not indicate with each other sample. So the time vector solves this problem by assigning a time value to every sample. The time values are calculated using sampling frequency during recording. So the signal was recorded. Okay, wait. So the signal was recorded at 44.1 kilohertz and the MATLAB will capture 44,100 samples every second. So therefore the interval between consecutive sample is 1 over 144,100. So the generated time vector serves several important purposes. So such as it allows waveform to be plotted correctly, provide the time reference required for carrier generation, and ensure synchronization between the different signal during the modulation. So without this time vector, the carrier signal cannot be generated because the carrier equation depends on the time. Okay, so this is very important. So therefore the time factor acts as the main part of the subsequent signal processing operation. So we are going for the next MATLAB code. This is for the time vector MATLAB. Okay, so this one we're going to explain line by line. So we are using length. So the length is t. Okay, so we are using example 220,500 samples for 5 recording. Okay, so 0 creates the 0 dash length voice that explains the creates the sample numbers. Okay, and it will converts the vector into a column vector. So fs stands for converts the sample numbers into the actual time values. All right, so we're going to go for the next slide. Okay, so the next slide is explaining on the generation of carrier signal. So this one explains on the one of the most components in this communication system. So in this amplitude modulation, the carrier systems acts as the medium that transport the information. Okay, sorry, if I'm blocking the slide. Okay, information from the transmitter to the receiver. So the carrier itself does not contain any useful information. So instead, it provides a high frequency waveform that can carry the voice signal during the transmission. So we have recorded the voice signal in this experiment, which contains the frequency below 4 kilohertz. So the signal frequency range cannot be transmitted efficiently over a long distance. Because why? Because they require a very long antennas and more susceptibility in the interference of the noise. So to overcome all of this problem, that is why this voice signal is combined with a higher frequency carrier signal. So the carrier frequency of the 10 kilohertz was selected in this experiment. All right. So, uh, so we are using a 10 kilohertz lah, okay, to provide the sufficient separation. So the carrier waveform is generated using a cosine function because the sinusoidal signals have constant amplitude and also constant frequency and also a predictable mathematical characteristic. So that is why these properties makes the sinusoidal signals ideals for the communication system. So before the modulation takes place, the carrier signals appears as a smooth periodic waveform. So unlike like the voice signal that we see before this, the carrier waveform does not contain any speech information. Its amplitude and frequency remains constant throughout the observation period. All right, so we're going to go through the MATLAB code. So the next slide is the MATLAB code for generation carrier signal. So this one we're going to explain line by line the same. So we are using FC1 10,000. So it defines the carrier frequency. So the carrier frequency is 10,000 hertz, or we can define as 10 kilohertz. So we are using 10 kilohertz. So why we are using 10 kilohertz instead of using different kilohertz? Because this 10 kilohertz, its the value is 10 hertz is below than 0 and it's more than 4. Okay, so why the carrier frequency must be higher than the voice frequency? For example, the voice frequency is 4 but the carrier frequency is 10. So why the carrier frequency must be higher than the voice frequency, which is 4? Because to get a better transmission efficiency, to get a clear frequency separation, to get an easier spectrum analysis, and also to get a successfully modulation. So the line number 2 explains that the carrier equals to cos 2 times pi fc times t. So this formula is actually to generate the carrier waveform. So why we are using cos? Because to create a cosine waveform. Okay, why we are telling 2 times pi? It's also to convert the frequency into the angular frequency. For example, omega equals to 2 pi f, where omega equals to angular frequency, f equals to frequency. Fc is represent the carrier frequency. So the carrier frequency is 10 kilohertz. T represent the time factor vector. So I think this you might get understand. Okay, so for this example, for this carrier signal, we can take from our daily life. If you cannot imagine in this topic, so you just imagine the voice signal is as a passenger and the carrier signal is a bus. So the passenger cannot travel without transportation. So similarly, this voice information needs the place on the carrier so that it can be transmitted. So the carrier provides a transformation medium for the information. So the expected output later you can see in the result, but the expected output we are expected to get a constant amplitude, a constant frequency, and also a smooth sinusoidal wave. Okay, so we are going to go for the next slide, which is amplitude modulation. So this amplitude modulation explains one of the important parts in this experiment. So the purpose of the modulation is to transfer the information contained in the voice signal onto the carrier signal. So in AM amplitude modulation, the amplitude of the carrier varies carry signal varies according to the instantaneous amplitude of the message. Okay, so before the modulation, the carrier amplitude is constant, the carrier frequency is also constant, but after the modulation has been done, the carrier amplitude has been changed, but the carrier frequency remains constant. So the voice signal controls how much the carrier amplitude increase or decrease. So when the voice amplitude become even larger, carrier amplitude increase, but when the voice amplitude becomes smaller, carrier amplitude is also decreased. So as a result, the information is contained in the voice signal becomes embedded with its envelope of the AM waveform. So the envelope is the outer boundary of the AM signal. So if the modulation is performed correctly, the envelope closely resembles the shape of the original voice signal. Okay, so a modulation, for example, we use a modulation index of 0.8 micro was selected because it provides a strong modulation and also introducing distortion. So we're going to go for the MATLAB command. So the MATLAB command that you can see here, we are using 0.8. As I said, why we use this, because it's much more stable. Okay, we define the modulation index as the first line is 0.8 micro. And why we use 0.8, because 0.8 value is bigger than 0 and is smaller than 1, so it means it's strong modulation, it's a clear envelope, and it doesn't have distortion. So the line number 2 explains AM signal equals 1 plus mu times voice, close the bracket, times with carrier. So this one will perform the amplitude modulation. So mu times voice is the scale of the voice signal. So the modulation index examines how the strongly the voice signal affects this carrier. So I think I have explained this part. Okay, carrier is also why they have carrier at the back of the code, because carrier multiplies the varying amplitude factor with the carrier signal. So this operation transfers the voice information onto the carrier. So the carrier sign is actually to multiply the varying amplitude factor with the carrier signal. So we have this AM equations signal is given. Okay, so you can see. Okay, so what will happens to the output? Okay, so the expected output we need a high frequency oscillation, we need a visible envelope, and also an envelope follows the voice of the signal. So we're gonna go for the next one is addition of AWGN noise. Okay, what is AWGN noise? So AWGN noise is additive white Gaussian noise. Okay, so we call it as short form AWGN noise. So this is during the transmission signal. Signals encounters various of source of interface such as thermal noise, atmospheric disturbance, electronic circuit noise, electromagnetic interference. So these unwanted disturbance are collected known as noise. So we don't want all of this noise. So that is why this AWGN is came to stimulate a realistic communications channel. So this we added this AWGN is added to the AM signal. AWGN is one of the most commonly used noise model in communication in our engineering field. Okay, so the term of additive means that the noise is directly added to the signal. The term of wide means that the noise contains a wide range of the frequency, which is similar to how white light can contain many colors. The terms of Gaussian indicates that the noise amplitude follows a normal probability distribution. So the purpose of adding AWGN is to evaluate how the AM signal behaves under a non-ideal transformation condition. By observing the noisy signal, it becomes possible to access the robustness of the communication system, and also is to determine whether the transmitted information can still recognize. So that is why SNR we have created around 2 dB. SNR is single to noise ratio is selected for this experiment. So this value introduces a noise while still allowing the signal remain visible and analyzable. So we're gonna go for the MATLAB. So this is the MATLAB for this question. So we're going to explain the MATLAB command for amplitude modulation. So we are using 0.8. As I said, 0.8 is your micro value. So it represents the modulation index, and this experiment we are using 0.8. So why we're using 0.8 also I have mentioned just now. Okay, so we use the command of 1 plus mu times voice, because this command performs the actual amplitude modulation. Okay, so we're going to go for the next slide. So the next slide is time domain analysis. So in this time domain, after generating all the signals, the time domain analysis is one of the thing which you will perform all to examine their behavior with respect to the time. So the time domain analysis is one of the most fundamental methods in signal processing lah. So the purpose of this analysis is to compare the different stages of the communication process and verify that each of them stage has been performed correctly. So just now from we have record the voice, we have run the code, the MATLAB code from recording until the time domain, until the AWGN voice code. So all of this code, after we press enter, 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 so we will get a output. We will get four output. The first output will get figure 1 is for the original voice signal. Figure 2 is for the carrier voice signal. Sorry, carrier signal. So figure 3 is for AM modulated signal. Okay. And figure 4 is AM signal with AWGN noise. Okay. So we're going to go for the first one is original voice signal. So this one, as I explained, we use a human speech to record naturally because the waveform appears irregularly rather than the periodic. Okay, so we're going to explain the MATLAB code. All right, so we're going to go by line. So the first line is figure is nothing. Okay, so the line 2 is plot T1 5000 times 1 5000 lah. So this command plots the original voice signal. So as we know, 5000 is the first sample that we selected for the time vector. Okay, T is contains the time value generated earlier. Okay, so we are only using 5,000 sample because the complete voice signal contains around like 22,220,500 samples. So for the 5-second recording, we cannot take all the sample. So that is why we just take only a bit. Okay, why we cannot take? Because then later the waveform will become more compressed and it's also difficult to obtain other details too. All right, so then later you can plot your x and y axis. So your x axis, horizontal axis is time, your vertical axis is amplitude, and you can you can just graph it lah. Okay, so I think this is clear. We can go for the next part. Okay, the next part is time domain for carrier signal. Okay, so this carrier signal is actually where it is plotted to verify. So this one is also you have a graph. Okay, just now's one also you have a graph. This one also you have a figure. You have a graph over here. You can see the result later on the result department. Okay, so this one is to verify that the sinusoidal waveform has been generated or not. So we're going to go through the MATLAB code over here. Okay, we want to explain. So we are going to go line by line. Okay, so the first line is figure. It's actually to generate the new figure window. Line 2, we use plot T1 dot 1000. Carrier also the same. So the plots of the carrier. So what is T1 dot 1000 is actually we select the first 1000 sample from the time vector. Okay. Okay, and also it contains the time values generation that we generate just now. Okay, we only choose 1000 sample because the FC equals to 110 kilohertz. So we have 220,000 sample. This if we put all the 220,000 sample, and I say it will make the graph more compressed and the characteristic cycle cannot be observed clearly. All right, so hopefully you guys understand this part. Okay, so now we are going for the AM modulated signal. Okay, so wait, let me check. All right, so the AM modulated signal is actually is to generated by the combined voice signal with the carrier signal. So this stage is one of the most important of the experiment because it's also demonstrate on how information can be transformed on a high frequency carrier for a transmission. So the amplitude modulation is the amplitude of the carrier which according to the instantaneous amplitude of the voice signal. So when the voice signal amplitude increase, the carrier amplitude is also increased. Similarly, when the voice signal amplitude decrease, the carrier is also decreased. So just now we have explained this one in our previous slide. So this is also the same thing. So the purpose of plotting this AM signal is to verify the voice of the information that has been transferred successfully into the carrier signal. So we're going to go through the notes a bit more. So although the amplitude changes, the carrier frequency remains constant throughout the process. So you can see the MATLAB code over here below. Beside that, it is a MATLAB code. Okay, so this is the MATLAB amplitude modulation for this one. So this one is mu. We are using sorry, not mu. I mean sorry. We are using line one. It's figure. Line two is to plot. So this one is to plot the AM modulated signal. As the same. We are just using the 5,000 sample. Okay, we can't use 220,000 sample. We do want this one to become compressed and difficult to observe the waveform. So your x-axis is the time and your y-axis is the amplitude, and you can put back the formula. All right, so line 3 is about the title, and also the output might be AM modulated signal. So that's your output. So the benefits, so I think we go for the next slide since we're gonna comes to the end. Okay, so the next slide is about AM signal with AWGN noise. Okay, so this one is actually after we generate from the AM modulating signal, the adaptive AWGN noise is been edited to this real communication channel. I think all of us know the purpose, because just now I explained. And also the purpose of analysis the observes is how noise affected in the transmitted signal. So by comparing the noise in AM and also the AM signal, the effect of noise on the signal qualified can be evaluated. So we're going to go through some notes on this. So although the noise introduces random fluctuation in the waveform, the envelope of the AM signal should still remain visible, because the selected signal to SNR, signal to noise ratio, is is high. So that is why. So we're going to go for the MATLAB command for this. All right, so we're going to explain about the AM signal with AWG and noise. So line 1 is figure. So the line 2 is plot T1 dot 5000. So as we know, 5000 is a sample. It's the same, why we are using 5000 sample, okay? And we are using 5 seconds for recording. That's why we write there 5. Okay, so if all the samples as plotted, why we do want all the samples to be plotted? Because later the waveform become compressed and all. It's the same reason with before the slide of this. Okay, so we are using noisy signal here because we are select the 5000 sample. So the variable is noisy underscore signal lah. All right, so it contains AM and also AWGN noise. Okay, this is not just noisy, it contains AM signal and AWGN signal. So therefore we stated as noisy underscore signal 1.5000. So it represents the AM waveform after the noise has been added. Okay. So the axis horizontal, we change it as time. Vertical is the amplitude. All right. So you can just plot out the graph over here. So that's all from my part. So thank you so much for listening. All right. So if I made mistake, hopefully anyone can just correct it. I'm so sorry. So we are moving to my next team. Thank you.
Frequency domain analysis using FFT. Frequency domain analysis using FFT. Fast Fourier transform, also known as FFT, was applied to both the original voice signal and the AM modulated signal. FFT is a mathematical technique used to convert a signal from the time domain into a frequency domain. The frequency domain analysis was performed to identify the dominant frequency components of the voice signal and to verify the presence of the carrier frequency and sidebands in the AM signal. So there are two steps. The first one will be FFT of voice signal, where the FFT was first applied to the recorded voice signal. This analysis was performed to determine the frequency components present in a human speech. And then the second part will be FFT of AM signal, where the FFT was applied to the AM modulated signal to observe its frequency domain characteristics after modulation. And then the resulting spectrum was plotted to identify the carrier frequency and the sidebands generated during the modulation process.
Hi, my name is Muhammad Hazim bin Ahmad Shairi, and my matrix number is B1224107749. and I will proceed to the next slide. So for my slide is experimental investigation. So let's get through. The modulation index, which is mu, controls how much the carrier signals can change in response to the message signal. Your three chosen values represent three distinctly different signal behaviors, each with real engineering consequence. So we see for the first is mu is equal to 0.3. So this is the under modulation. The message only slightly varies the carrier amplitude. The signal is safe but inefficient. Most of the transmitted power stays in the carrier, not in the sidebands sideband that carry useful information. Low bandwidth usage, low risk distortion. So we look to the next is mu is equal to 0.8, which is the optimal modulation. The sweet spot in practical AM system, the signal power is well distributed between carrier and sidebands. High finely, no distortion, efficient use of bandwidth. This is what broadcast radio engineers target. And next, we go through to the mu is equal to 1.2. Then it is the over modulation. The message signal amplitude exceeds the carrier. This causes envelope clipping. The waveform invert during negative peaks, creating distortion and harmonic interference. Not visible in standard AM without special technique like DSBC, and it important to study as a failure mode. So for each value, the modulation process was repeated and the resulting waveform were compared. Okay, we've talked about theory, but now we see what actually happens when we run this MATLAB command. So the first thing first we do is to set our modulation index. Mu is equal to 0.3. Remember, mu tells us how much does the message signal change the carrier. At 0.3, the answer is not very much, only 30%. So for the first part, which is now this is one line here is the heart of everything. So it's very important, which is the point to the AM signal 03 is equal to 1 plus mu times x times carrier. Breaking into two parts, the first part is 1 plus mu times x. This build envelope, think of it like slowly moving boundary at mu is equal to 0.3. The boundary only moves between 0.7 and 1.3 is very small range. The second part, multiply by carrier this stem that envelope onto our high frequency carrier wave. That's the actual modulation happening right here in one line. The dot times moment make it memorable. One thing I want you to notice is the dot before the multiply sign in MATLAB is dot times means multiply element by element one sample at a time. If you forget the dot and just write the star, MATLAB will try matrix multiplication and give you an error. Small dot, big difference. So we need to take note about the dot and a sign of star. Okay, now I will explain the plot command. Then we plot. But notice we only plot the first 5,000 samples, not the whole signal. Why? Because if we plot everything, the waveform would look like a solid black blob. 5,000 samples give us just enough to see the carrier oscillation and the slow envelope movement at the same time. So describe what the audience. So when you look the resulting waveform, you'll notice the outer boundary of the wave barely move. It looks almost like uniform wave with very slight thickness variation. That is visual signature And under modulation, the information is in there, but it's weak. If you were trying to receive the signal, your detector will pick up a very faint message. So, mu is equal to zero point 0.3 is our baseline. It's safe. No distortion, clean signal, but it's inefficient. Most of the power is sitting in the carrier doing nothing useful, and that's exactly why we're going to compare it with mu 0.8 and mu 1.2 next. So we go to the 1.2. So we see mu 1.2 is which was too weak, and mu 0.8 which was just right. Now we're going through the rule on purpose with setting mu to 1.2. Look at the code. It almost identical to before, same formula, same plot, command, same labels. The only thing changed is the first line, which is mu is equal to 1.2. The everything command is still remain the same. Okay, let me explain. Here is the key question. Why is the 1.0 the magic number? Remember our envelope formula, 1 plus mu times the message. When the message signal swings negative, which is always does its sine wave, you get 1 minus mu. At mu 0.8, the minimum is 1 minus 0.8 is 0.2, still positive. Envelope stay above 0 clean signal. At mu 1.2, the minimum is 1 minus 1.2, negative 0, 1.2. The envelope tries to go below 0 and that the physically impossible for standard AM. The signal inverts, it flips, and we call the clipping. So when you plot the signal, you'll see something strange. The waveform looks normal for most of the cycle, but at certain points, the wave suddenly pinch inward and cross over itself. Like the envelope collapse and inverts, that pitching point is exactly where the envelope tried to go negative. Now, why does this matter practically? When the signal clips like this, it generates new frequencies that were never in the original message. These are called harmonic distortion. They spill into neighboring channels, meaning your signal start interfering with someone else's broadcast. That's why in real AM radio that's why in real AM radio system, regulators strictly prohibit mu from exceeding 1.0. It's not just bad engineering, it can actually be illegal. So why did we deliberately create this bad condition in our experiment? Because seeing the failure mode is just as important as seeing the ideal case. When you understand what breaking looks, you understand why the rule exists. And in real engineering, knowing when how a system fails is half the job. Alright, so our methodology part is about to end. So I will pass to my friend for continue our slide. Thank you.
My name is Punithan Krishnamurthy. So now let's move on the result. I go through each graph one by one. This is the original voice signal we recorded using a microphone. The waveform looked very different and irregular because real human speech contains many different frequencies mixed together. And the amplitude is extremely small, which means the signal is too weak and too low in frequency to be transmitted over long distance without any processing. This is the carrier signal, which is a pure constant wave at 10 kHz frequency. It has contained the amplitude and frequency. It carries no information at all. Its job is simply to add extra, recycle that transport or voice signal to the receiver. We choose 10 kHz frequency because it's much higher than the voice frequency range. This is the AM modulated signal at modulation index micro 0.8. After combining the voice and carrier, you can see the amplitude of the signal is no longer constant. It rises and falls according to the voice signal. The outer boundary of the waveform is called the envelope and it follows the shape of the original voice.
This confirms that the voice information has been successfully embedded to the carrier signal. AM signal with noise. Here we added additive white Gaussian noise at 20 decibel signal to noise ratio to simulate a real communication channel. Compare it to AM modulated signal graph, the waveform look rougher and more irregular. However, the envelope shape is still visible, which means the voice information can still be recovered at the receiver even under noise condition. This graph shows the frequency spectrum of the voice signal after applying fast Fourier transform. Most of the signal energy is concentrated below 500 Hz, with some component extending up to 4 kHz. This confirms that the human speech is a low frequency signal, which is why modulation is needed to shift into a higher frequency before transmission. Fast Fourier transform of AM signal. After modulation, the frequency spectrum looked completely different. Instead of being near 0 Hz, the energy has shifted up to 10 kHz. The dominant spike at 10 kHz is the carrier, and the smaller component on the both sides are called sideband. The sideband actually contains the voice information. This is the main purpose of AM modulation, to shift the signal to a higher frequency suitable for transmission. We compared three different modulation index values to see how they affect the signal. So this one is micro 0.3. So in this graph, the amplitude variation is very small, the envelope is weak, and the voice is not efficiently represented. This is called under modulation. At micro 0.8, the envelope clearly follows the voice signal shape. The modulation is clean and efficient. This is our ideal condition. At micro 1.2, the envelope becomes distorted and no longer represents the voice accurately. This is called overmodulation, and it causes signal distortion, which makes it harder to recover the original voice at the receiver. So, the result clearly show that AM modulation successfully shifts the voice signal to a higher frequency, and that choosing the right modulation index is important to maintain the good signal quality.
Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hatta Hafiz bin Masli. Now I will present the discussion analysis for our report. First of all, the comparison between original and the AM signal. The original one has low frequency, it's irregular because it's a real speech signal. For the AM signal, it has high frequency carrier carrying voice through amplitude envelope. Modulation makes the voice signal more suitable for transmission. For the time domain analysis, voice waveform changes naturally with speech loudness and pauses. Carrier has constant frequency and amplitude. AM waveform shows carrier amplitude with varying with the voice signal. For the real voice, it is more complex than the sine wave because it contains many frequency and irregular amplitude changes. This makes the experiment closer to real communication system. For the overall analysis, AM successfully shift voice signal to higher frequency. Proper modulation also preserves void information. Noise and overmodulation reduces final signal quality.
Alright, so for the conclusions, this project successfully simulate an amplitude modulation, which is AM, communication system in MATLAB using a real 5-second voice signal to demonstrate practical telecommunication principles. While an unnormalized audio amplitude vector caused a visual scaling anomaly across the under, proper, and over modulation time domain plots, which is 0.3, 0.8, and 1.2. The underlying mathematical mechanics of standard AM were correctly structured. Furthermore, fast Fourier transform (FFT) analysis explicitly validate the frequency translation process by displaying a distinct spool of 10 kHz carrier peak flanked by symmetric upper and lower speech sideband. Finally, evaluating the system under additive white Gaussian noise, which is AWGN, at the end signal noise noise ratio of 20 dB confirmed that despite visual high frequency distortion from channel impairment signal and wave and envelope integrity were robustly preserved for successful message retrieval. So that's all from us. Thank you for your attention. Thank you.